Today we're talking about orbital angular momentum. It's just like a regular angular momentum, except instead of J, we call it L. But it's the same kind of object. It's got the same eigenvalues and eigenstates. We'll just see an interesting subtlety that we can't have half-integer orbital angular momenta. So that's kind of interesting. It means that angular momentum associated with actual factual motion that only has integer eigenvalues, doesn't have the funny spinner type representations. So, and that, we'll see why that kind of makes sense. It won't be a formal proof or anything, but where we left off last time is the idea that orbital angular momentum has to do with rotations in actual space. So we're considering rotating our coordinates to, here's a rotation around the z-axis. And we're leaving this up here. We'll refer to it in a moment, but we're leaving this up here because it's sort of, it'll be convenient as an expression. So of course, if we're rotating around z, the z doesn't change. Okay, so we have this rotation around the z-axis, and it'll be useful for what we're doing. And where we left off last time is we were trying to understand if a wave function, which in this rotated frame, we were trying to see if it picks up any kind of phase when we rotate. And so the rotated wave function, the wave function rotated frame is the wave function in the old frame that's not rotated, evaluated at the inverse rotation operating on the coordinate. And we were just wondering, is there this phase? And if there is, then you might, think that there should be something like a spinner type representation. Perhaps you can, the rotated wave function might pick up a minus sign if we rotate by 2 pi, but we'll see that that's not possible for coordinate rotations. It's only possible for internal degrees of freedom to spin. Was there a question? No. Okay, so what we were doing is we were looking at the coordinate operator. And we were looking at the rotated, we were trying to see if the coordinate operator, if its components, if we take a rotation is implemented by a unitary, it's hard to, there's multiple r's running around, but this is a rotation. And we're applying it to some coordinate, right? And we're asking, is this thing, this object, is this still an eigenstate of position? That's what we're showing. And you can show that it is, because you can take this unitary, and of course you can add a UU dagger, or UU inverse, because it's unitary. And then we have this RK, and then we have the U again, acting on the R. This is just the identity, so we can stick it in there, it's easy. But now we make use of the fact that the coordinate operator is a vector operator. So it rotates just like a vector would. So what this is, it's U, and then this is a sum over J of the rotation matrix here. I guess it's KJ. It's a little bit funny. I don't know how to do this notation properly. I so this is like a curly R, maybe this is the rotation matrix. It's just, there's too many R's running around, but that's just the way it is, I guess. And this is our RJ, this is the position, it's a component of position, like XYZ. All right, and this is all acting on R. So we're just replacing this guy with this, because that's the definition of how a vector operator works. A vector operator is defined as something where you take U dagger, the vector operator component U, and you get back out the rotated components. So you see, now this is an eigenstate of these guys. So this all comes out, and you get that this is U. And now this is just sum over J, the rotation matrix, Kj, little rj. These are the numbers that, you know, this is the eigenstate of position. So these are just the eigenvalues, the actual rotated coordinate acting on R. So you see, this is just a number now, and so it can come out. And so what you find is that this is a rotated coordinate, and this is U of R. So this is what we started with. So now you see, indeed, this guy, right? It's an eigenstate of this operator, still an eigenstate of position. The eigenvalue is just the rotated coordinate. So we can, and there's no extra phase running around. It's just purely, the eigenvalue is just the rotated coordinate. And so it means we can define really the rotated ket as, you know, it really is just the U operator corresponding to rotation acting on the coordinate. So now it's okay, and there's no extra phase that comes up, nothing like that, because of this property that R is a coordinate operator, so it's a vector, and so it transforms this way with no extra phase or anything like that. You see, it basically, so orbital angular momentum has to do with actual coordinate rotations, motion in space. And so the coordinates themselves, right, are vectors. So they transform like vectors, they rotate like vectors and not like spinors. And that's really the fundamental reason why you can't get half integer angular momenta, right? It's always the integers, because the coordinates themselves are vectors, they're not spinors. So that's basically the idea of this little calculation here. And now you can see, you know, you can use this now, right? You can use this, for instance, to understand this rotated wave function, right? What's the rotated wave function? Well, it must be the coordinate representation of the rotated state, right? This is your original state, then you rotate it. This is your state, then you rotate. And then you do the coordinate representation. And so we can act with the U on the left, and that gives us a U dagger acting on R. So this is the same as the inverse rotation operating on R, acting on the state. And so this is the original wave function with the inverted rotation acting on the coordinate. So that's really, hopefully now it all comes together. You see how it all fits. Right. Okay. Any questions about that? No? Okay, very good. So let's look at a particular rotation. Let's look at a rotation around the z-axis. We'll call it phi for the polar angle here. Incidentally, I'm using units where h bar is equal to 1. So I'm not dividing by h bar or doing anything like that. So in this case, the canonical, the commutation relations of the angular momentum components are as follows. If you wanted to stick back in the h bars, you would just recognize that whenever you have a j, you have a unit of h bar, because j has units of h bar. So inside the exponential, you would cancel this h bar unit by dividing by h bar. Here, there's two j's over here, but only one over here, so you need an h bar to fix it up. But it's just inconvenient to keep h bars everywhere, and it's better to just leave them out and then put them in at the end if we want, or you don't have to, but it's just a convenient system of units, or you just set h bar equal to 1. Should get used to it. If you ever take quantum field theory, they set everything to 1, including the speed of light and so forth. Okay, so let's look at this rotation. If we expand it around small angles, as we do, then yeah.
I did have a question about that. I am in particle physics. We set h as 1, c as 1 because they're natural units, right? But in classical mechanics last week, not last week, a couple of days ago, he was going over it with us, saying that it's like a transformation. So you're saying that in actuality, to get h bar back in there or transform it back into the, I would just have to divide it, the exponential h out, because j has the units of h bar. And what did you say about the phi inverse r again? Where was the h bar in that one?
It's nowhere in here. It's just whenever you have j has units of h bar, so you have to make sure that the numbers of j's and h bars balance out. And if you ever have an exponential of something, an exponential of anything is always unitless. You never have units inside an exponential. So if you see a j, then you're like, oh wait, that's not good because that has units, so you have to divide by h bar.
I see. Okay. All right. Thank you.
Okay, so let's look at a rotated state for small phi. For small phi, that would be the identity minus I phi jz acting on our wave, the state. And we're just going to look at this rotated state, as a function of r. So just this guy, right? So it's u of r acting on psi, and we're looking at the coordinate representation. So we know that that has to be, right? What is that? Well, it has to be psi at the inverse rotation. So if we look at, now we can go back here and look at this guy, right? We can look at these components right here. If we look at this for small angle phi, this becomes x. This becomes minus y phi, but we're looking at the inverse. So we just take the phi to minus phi. So this becomes a plus y phi. So the first argument here is x plus y phi. The second argument is x minus x phi plus y. And the third argument is just z. And now if we Taylor expand the function, right, we're going to linear order in the phi's, right? That's always what we do, expand to leading order in the phi, like a Taylor series. So we have to Taylor series this now. So this, is approximately equal to phi, the original phi at the original coordinate, plus the linear terms, which are y partial x psi minus x partial y psi. Why? Because you can see that the y here's if you Taylor expand this, right? This is in the x component, so this is along the x direction. This is the little perturbation, y times phi. Along the y direction, so the Taylor series component, along y, that's minus x times phi, so that's this term right here. And this is just the Taylor series of this function, expanding around phi equals 0. These are this is the first term. You might want to review multidimensional Taylor series, right? Like expanding a function, a vector function, right? Like this, it's psi of r, then it's delta dotted into the gradient of psi, and so on. Might want to review that. It's helpful. Yeah, if you don't remember your multivariate calculus. Okay, so you have this. And this is a combination of position and momentum, right? The derivatives are going to be momentum with a factor of I. See, there's a factor of I over here. See, now we can compare, right? This and this, because both are linear in phi. So we conclude from here that JZ is, or JZ acting on psi is XPY minus YPX. The little I here gives us, you know, we can multiply both sides by I, and then we would get the momentum operators. Again, H bar is 1, so there's no H bar. So this just becomes XPY minus YPX acting on psi. And if you think about what that is, that must be the Z component of the vector R cross P acting on psi. And what is this? This is nothing but the angular momentum along the Z component of angular momentum acting on psi. So there you go. We have now shown that, and that's what, you know, that must be what it is, right? Because that's the J, right? The J, we're just replacing J with L, just, I don't know why. I mean, you could call it J, but whenever it's orbital, whenever it has to do with motion in coordinate space, like you call it L instead of J. I don't know why. So we see here that L, the angular momentum associated with, you know, coordinate rotations, that must be equal to R cross P. Now it's explicitly, you can see that it has something to do with motion in space, right? It's the coordinate operator crossed with the momentum operator. And of course, this has, just like J, has angular momentum states Lm. And now L, instead of having half integers, it can only have integers. Right, but otherwise it's exactly the same. And we can figure out how the components of angular momentum act on wave functions. Or, you know, since we're in coordinate representation, these operators must, you know, behave like derivatives. So we already see how in the Cartesian coordinate system, this is what LZ does, right? It does this cross product kind of thing. Of course, it's easier in spherical coordinates because if you take e to the minus I theta LZ here, acting on psi in spherical coordinates, then what this should do, right, is just rotate the thing around the z-axis. So it should, I shouldn't call this theta because theta is the kind of angle away from the z-axis. So we call it alpha or something. This should just rotate us like that. So we see then that, you know, for infinitesimal rotations, this is just, you know, minus alpha derivative with respect to phi of psi. So this here must correspond to what LZ actually does. So we see from here that LZ, by comparing, you know, we can expand this around small alpha on both sides, compare the two things, we'll see that LZ must be minus I, and it's the derivative with respect to the phi angle for, you know, spherical coordinates. Yeah, so again, so phi is like this angle around the z-axis, and theta is, you know, angle away from the z-axis. So that's what LZ does, and now you can do a similar thing, right, to see what happens to rotations around the other axes, right? You could rotate around X and Y and so forth, right? And then you would have exponential of X and Y, and then you could calculate using properties of rotations what it does to this function, rotation around X and Y. And then you could again Taylor series around small angle, and you could extract what LX and LY do. And that's sort of, that kind of calculation is what sort of you'll be doing on the last homework. And I'll just summarize the results here. This, I've already showed you that LZ here is minus I, you know, partial with respect to the phi. And now you can have the equivalent of the J plus minus, right? It's the J plus minus, which are the LX plus or minus I LYs. Those are given by I, E to the plus or minus phi. It's the cotangent of theta, and it's the derivative with respect to phi, and it's plus or minus I in the derivative with respect to theta. It's a little bit tedious to show these, but it's just properties of rotations that allow you to conclude these things. Again, you could, it's the same kind of thing here, except it's more complicated because when you rotate around X and Y, both of these angles, you know, rotate around. So it's a little bit tricky, but you can get this.
Could you label the axis over there?
Okay.
Thank you.
So yeah, and also there's L squared. That's minus 1 over sine theta. That gives you that. This is the angular part of the Laplacian in spherical coordinates. And this will be important because a lot of our Hamiltonians have this operator in it. For any spherically symmetric Hamiltonian, just has a Laplacian in it. The angular part of it will be L squared. We'll see that later. Yeah, but you'll show this. But in terms of, these expressions are not so important. What's important is what I told you about these operators last time. What I showed you is how they raise and lower these actual eigenstates, right? That's what's important about them. But in everything else, you know, it's sort of the same. It's just, you know, LZ acting on LM gives me M times LM, and you know, L squared acting on LM is L plus 1 LM. And when we raise and lower these LMs, you know, you get those normalization factors with the square roots. So, okay. Again, this is not so important, but we'll look at it in the homework. It's just, you know, these are just the raising and lowering operators for angular momentum. This is the angular momentum squared. Maybe I should put a little vector here, and this is the z component. And, you know, they have some representation in spherical coordinates. This is what the operators look like in coordinate space. This is how they act on wave functions. That's, and you know, I showed you the z one, and you can show this one. It's more complicated, but it's not that bad. Okay, so what about the angular momentum states, what's the wave functions associated with that? Does anyone know what this is? What functions these are?
Sorry, I was answering an email. What was your question about? What kind of wave functions or what again?
What are the wave functions corresponding to the eigenstates of angular momentum? What's this?
I know them too. I'm sorry. I'm having brain fart. I just taught the angular momentum, though the orbital states are the ones above you, to my students. So I know that
Is
part.
it the spherical harmonics?
Yeah.
Yes, that's the spherical.
Spherical harmonics.
These are the YLMs, right?
Yes.
The coordinate representation of the eigenstates of angular momentum, they're just the spherical harmonics. So, yeah, and then everything else just operates like the states we were looking at before, the JM states. It's the same thing. It's just instead of J, we call it L. I think it makes it unnecessarily confusing, but that, this is just the coordinate representation of those states. Those are spherical harmonics.
That is confusing though. I mean, like you said, when we start mixing things like that, even though it means the same. So
it means exactly the same thing. Yeah, it's weird. We should have just called everything J, and then maybe people would be less confused. And we call it L.
Yep.
When you see L, you just think it's J, but only with integer values for the.
Yeah, the L plus 1 thing. Yeah, it has to be. All right. Yeah, but you're saying H bar is 1 here too, right? Every time you see a J, are you saying always up on top with the angular
Yeah,
orbital?
H bar is 1 for these.
Because there is a H over 2 pi time squared for the integer values, I thought, somewhere here. Anyways, or H
there's
bar.
no energy. It's just, yeah. If you want to stick in the H bars, there'd be an H bar here, and there'd be H bar squared here.
Yeah. Okay. That's fine.
Okay, so this is all very useful because oftentimes you get Hamiltonians. So you get energies that just depend on angular momentum, motion. Like you might have a little dumbbell or something that's rotating around with it has some angular momentum L. And the energy associated with that would be, L squared divided by 2I, where this is the moment of inertia. And as soon as you see this, you know immediately what the eigenstates are. You know what the eigenstates are. You know what the eigenvalues are because you already know everything about angular momentum. So if you see this, you say, oh, look, this is L squared. We know how to diagonalize that. We just use these LM states. And these LM states have eigenvalues, H bar squared, L plus 1. Or if you don't have the H bar, just L plus 1. So you know that the energy levels are going to be labeled by an integer L, and they're going to be, L plus 1 over 2I. And if you really want, you could put it back in the H bar squared. And L would be, 0, 1, 2, and so on. Those are the energy levels of a little rotator, a little dumbbell with moment of inertia, I that's sort of rotating around. And the eigenfunctions will be the spherical harmonics. And you even know what the degeneracies are for each L level. There's a 2L plus 1 degeneracy because of the M's, right? There's 2L plus 1 M's for each L. So you immediately solve any kind of problem that involves rotation in it. You have any kind of Hamiltonian that's just the angular momentum squared, and then, it's just the rotational kinetic energy, then you immediately know how to solve it from what we know about angular momentum. Okay. So any questions about this? Okay, so now we're gonna go over here and think more about these spherical harmonics. So they're the eigenstates of angular momentum. And again, angular momentum, Hermitian operator, you know, so these form a basis, right? So the spherical harmonics actually form a basis for any square integrable function of two angles here, the spherical coordinates. So any function on a sphere can be expanded in the spherical harmonics. So you immediately get that. You also get that they're of course orthonormal, meaning that if you dot two of them into each other, which would involve integrating over the surface of the sphere, which would look like that if you take a YLM of theta phi and multiply it by, oh, here's a star, right? The inner product of another one. So the Y L prime M prime theta phi. Well, then you should get that this gives you, right, Kronecker delta. So they're normalized like that. And if you wanted, you could, again, expand any function of theta and phi, as I said, into a basis, you know, spherical harmonics. So these are the YLMs, theta phi, and then each coefficient would just be an integral, and it's often convenient to denote all of these by a d omega, because you don't want to keep writing out all the angles. And these coefficients here would be d omega. Let's make it a prime here of y lm omega star f of omega prime. So it's the inner product between f and the YLMs. These are just the coefficients, right? This is like the CLMs corresponding to an expansion in spherical harmonics. It works as a basis for the space of functions, the space of square integrable functions on the sphere. What else? You can do a kind of analysis of what the spherical harmonics have to be. That's quite similar to the way we derived the way we thought about the eigenfunctions of the harmonic oscillator, where I don't know if you remember, we found like the lowest, the ground state energy, and then we use the raising operators to construct the other wave functions. And you can do the same thing here using these guys, right? These raising and lowering guys, we can act with them on the angular momentum states to see how to construct basically the spherical harmonics for any L and M. And I won't really go into it, but because it's not particularly important, but basically what you find is that instead of Hermite polynomials, so for the harmonic oscillator, we had Hermite polynomials as what happens when we kept acting with the raising operator on the ground state. It kept getting derivatives of a function, of the ground state function, and then that generated a series of polynomials. Well, for angular momentum, you get a different set and those are the Legendre polynomials. But it's just a little bit tedious to derive them. So maybe I'll do it in recitation at some point, but it's not particularly important. But the Legendre polynomials are given by, so this is just some function u. It's going to turn out to be cosine theta. You know, the same theta as here, the polar, the spherical coordinate. But the polynomials themselves look like this. Their derivatives is promised with respect to u, L of them acting on u squared minus 1 raised to the L power. So they're just some polynomials. There's also the associated Legendre polynomials. That's when you include the effects of having an m. These are called the associated. And those guys are given by 1 minus u squared m divided by 2. And now it's m derivatives acting with respect to u acting on these guys. So these you would get by, you know, acting with the raising operator L plus. So they're just some polynomials that you can derive using something that's quite similar to the way we derive the eigenstates of the harmonic oscillator, but it's more complicated because you have two quantum numbers here, L and M. I won't do this, it's a little bit too technical, but in the end, what you can show is that the spherical harmonics are given by what? They're given by minus 1 raised to the m power. There's a funny normalization, 2L plus 1 over 4 pi, and L minus m factorial, L plus m factorial. And you have these associated Legendre polynomials of cosine theta. And then you also have the part that depends on phi. That's e to the im phi. So the phi part is very easy, and often in problems, all you care about is how it depends on phi. So it's very important to keep in mind that this is the way it depends on phi. It's just a little exponential of im phi up here. Oh, and these are for positive m. For negative m, you get that it's minus 1 to the m, and then it's the same as the positive m's, but it's complex conjugated. So these are the spherical harmonics. I've sort of given you the recipe of how to write down explicitly in terms of theta and phi any spherical harmonic. Now it's a gross recipe, it's not particularly helpful, but this is just what it is. And again, I don't want to derive it because it's kind of complicated, but I just want you to remember how we did it for the Hermite polynomials for the harmonic oscillator. If you go back to those notes, how we constructed those by using the raising and lowering operators on the ground state. You can do something quite similar for these guys. Maybe if you read it about it in a book, maybe I'll do it in recitation. Just important to keep in mind that analogy between the harmonic oscillator and the angular momentum. It's the same thing. We're working on a ladder, and we're just trying to figure out the rungs of the ladder, the functions corresponding to each rung of the ladder, by applying the raising and lowering operators. And the raising and lowering operators, they do some derivatives. They you know, they act like with these derivatives. And so you can, if you start with one of the rungs, like the bottom or the top rung, you can construct all the other rungs by acting with those derivatives and seeing what happens. And that's basically how you get formulas, these formulas for the Legendre polynomials. But I don't really want to get into it too much, maybe for recitation. But the point is, you can explicitly write down what the spherical harmonics are doing that kind of thing. Any questions about that? Hopefully you've seen spherical harmonics at some point somewhere else.
Yeah, they're in you know, in E&M under the
Yes.
in greatness and everywhere.
They are everywhere, yes, that's true. But now you know this different way of thinking about them, and you know, probably in other classes they were just also like I did here, they were just handed to you and said, oh, here they are.
Oh yeah,
and
that's
I did
exactly
the
right.
same thing, but I at least gave you a hope of being able to derive it from scratch, right?
Yeah, you gave us a little bit more, but you said in recitation you might go over a little bit more
maybe
detail.
I'll derive, you know,
Nice.
derive how you actually can construct them.
That could be very valuable for YouTube, because a lot of people, you know, when I was doing them, I'd have Googled that and that would have been very helpful.
Yeah, usually you just Google them, right? And yeah. You just read them off from the table or something. But
yeah,
you can, you know, if you're stranded on an island, you could, in principle, reconstruct them just from what you
nice.
know about angular momentum.
Yep.
Of course, you'd have to know how these operators behave in coordinate representation, but I'll show this in recitation too, I suppose. We could do that. That could be like a long recitation, maybe.
Cool.
Okay. So that's good. So now we have them. Let's look at some examples. You know, you have this recipe and you can like use it. So the one of the most common ones is the L equals 1 spherical harmonics. So there should be 3 of them, right? For the 3 values of and unsurprisingly, they're going to be related to the components of the position coordinates. So if you work it out, the 0th one is square root of 3 over 4 pi cosine theta. And that's like the z component of the coordinate vector. So if you have the unit vector, this is sine theta, cosine phi, sine theta, sine phi. This is cosine theta. So you see, you got this guy. If you take this guy minus 1, well, let's just do plus or minus 1. Just do both of them for m equals plus or minus 1. This guy is minus plus square root of 3 over 8 pi, either plus or minus I phi. Again, it's this I phi that's important. Again, plus or minus m. It's always, you know, either the I m phi. So if it's plus or minus 1, you just get this guy. And the cosine part is the sine theta. And you see, these guys are just combinations of cosine and sine phi. So you can actually rewrite this as plus or minus square root of 3 over 4 pi of Rx, the x component, plus or minus I r hat, the y component, you know, divided by square root of 2. Yeah, so they're just the components of the unit vector corresponding to the position rotated into each other. And so this is often what you do when you have any kind of problem. You'll practice this on the homework. When you have any kind of problem with some wave function that depends on angles in some way, right? Like on the homework, you'll be trying a wave function that has like a That's some normalization times sine squared phi. Whenever you see anything like that, what you want to do is rewrite this until you get it to be just in terms of the spherical harmonics. But often you don't even care about the theta part. You just want to get it in terms of e to the plus or minus im phi. And that lets you interpret a wave function, right, as a linear combination of, as an expansion in terms of the LM states, right? We want to be able to write this, right, as some coefficients of the YLMs. And that lets you kind of understand various things about it, like what's the average angular momentum of that state? Or, you know, what are the possibilities for measuring a particular angular momentum? And the way you do it is, again, you expand this sine squared phi in terms of these e to the I phi. So you already know how to do that. You know, just expand sine and the complex exponentials. You square it, and you get some cross terms and so on. But that's sort of the procedure. So oftentimes you get some function with some angular dependence. You decompose it until you can read off the individual components with particular m values, and then you can sort of back out, what the component states are in terms of the angular momentum. So that's basically how it works. What else? You can, of course, rotate the sphere. So let me clear this, I guess. Any questions, though, about that? Yeah. That's weird. Okay, so you can, of course, rotate the YLMs. Nothing particularly surprising about that. This is just a coordinate representation of the angular momentum states. So if you rotate them, which again, you would have the inverse rotation of the argument. And again, I'm going to put this omega, this is just the angular coordinates, theta phi. So those rotated guys would be, unsurprisingly, the D matrix elements, right? The D matrix will tell you how these things rotate. All right, where this is that Wigner D matrix that we looked at last time. And you can actually connect, right, the Wigner D matrices to the spherical harmonics themselves. So the dm0 L spherical harmonics, as a function of the coordinates. Remember, these are the matrix elements of the exponentiated angular momentum. So you can actually use then the spherical harmonics to derive that this is just 4 pi over 2L plus 1 YLM theta phi star. So you can connect these elements of the D matrix to the spherical harmonics themselves. Let's see, what else? So let's talk a bit now.
Can I, so in that, I don't mean to interrupt you, but
No,
that omega again was our shorthand for that. Since we're doing spherical harmonics, that was shorthand for sine theta phi thing, right?
Yeah, it's a shorthand for the spherical coordinates
Okay.
theta and phi. Yeah.
That's right. Okay. I just want to make sure. Thank you.
Yeah, and this is exactly what we were looking at before, when we were looking at taking a rotated LM state, right, and writing it as a sum over L prime, that's those Wigner D matrices. This is obviously the spherical harmonics have to rotate in exactly the same way because they're just the LM states, but in a coordinate representation, but they still rotate the same way. So you still use those Wigner D matrices to rotate them around. And you can use the spherical harmonics, right? Because the D matrices are just the matrix elements of the exponentiated angular momenta. You can actually just then derive how the D matrices, this is just the zero component here, is associated with the spherical harmonics themselves. So there's lots of different kinds of
And that star means
games you can
complex
play.
conjugate as
Sorry?
well. You're saying that star there is the complex conjugate of this
Yeah,
thing?
you have to take the complex conjugate of this YLM. There's lots of different funny properties you can prove that connect the spherical harmonics to the Wigner D matrices. Maybe we can talk more about it in recitation or something. You'll be practicing a little bit of that on the homework, well, not much. As I said, the field of angular momentum, in quantum mechanics is a huge field. There's an entire book, it's Edmonds, that, just goes into this and,
Does it
huge
derive
amount of
it
detail.
specifically and stuff? So it does step by step in the book, kind of gives you an overall view of how to do it? Or is it just talking about it?
There's just so many different identities and things you can prove about, rotating spherical harmonics. And
So he shows the proofs though, Edmonds does?
yeah, for some of them, yeah.
So is there like, I guess this is kind of off topic, not about the proofs, but is there like a book out there that that actually shows proofs and not just, oh, you need to try to prove this, but actually has proofs for this stuff?
Edmonds does a pretty good job. This is the classic text, I would say, for this topic. I don't know.
Edmonds.
Any quantum mechanic book will have proofs of some subset of these things.
Yeah, they have just small proofs. Yeah, I thought there may be like a big book of proofs or something.
No, I don't know anything like that. But
yeah,
this book, Angular Momentum and Quantum Mechanics, this is sort of like a very classic resource that you might look at for this stuff.
We have this break coming up, so.
Yeah, well, this is a classic book, but it's just a huge field, so I'm just giving you like a little bit of just some formulas that you can derive. I still haven't decided which particular ones we're gonna look at. I mean, maybe I'll mention some of them for the extra topics that we discuss if people are interested in angular momentum, but it's not particularly important, I don't think. The important thing is up here, right? That that when you rotate the angular momentum states, they rotate with these D matrices. And then that the coordinate representation of the LMs are just the spherical harmonics. And starting from those two facts, and then just, of course, and recognizing that these D matrices are just the components, in terms of LM of rotating by by theta, around the y-axis, and then by phi around the z-axis, right? That's what this is. Those two facts alone sort of give you everything you need in a sense. It's just tedious algebra from them, but those are the concepts I really want you to absorb, I guess. And then the calculation stuff, you know, you'll practice a little bit on the homework, but not too much.
Yeah.
Okay, so where I wanted to go now is how do you use all this stuff? And you use it to study, of course, you know, things like radial potentials. Or, you know, 3D stuff. You do 3D quantum mechanics. That's where it really comes in. Because in 3D, you know, you have your kinetic and your potential energy. And often this potential energy is spherically symmetric. And that's really where the angular momentum states really come into their own, is for Hamiltonians like this. Why? Because if you take the p squared operator, right? That's in 3D, that's the Laplacian. That's minus I gradient squared, right? The p operator, again, h bar is 1, so there's no h bar, but this is just the gradient squared. So and if we put a minus sign here, a minus sign there, then this I squared gives us a minus, and this minus here, and it just gives us the Laplacian. And then you can go in, you know, a book like, you know, E&M book or whatever other book that gives you what this is in spherical coordinates. And what you would find is that it's looks like this. I'm writing it, so this is you multiply by r, and then you take two derivatives and you divide by r. And then there you got this part. And now this is going to start to look vaguely familiar because I wrote this down before. Right, this is just this is L squared. Yeah, or actually it's minus L squared. So all of this is 1 over r, two derivatives with respect to r plus 1 over r squared L squared minus. So any three-dimensional problem like this, you know, the kinetic energy part is going to be a combination of a radial piece plus an angular piece, which is proportional to L squared. And there's this 1 over r squared running around. But we already know how to diagonalize this piece. So you can reduce a 3D problem to a 1D problem by simply diagonalizing this piece, right? And then just having some piece left over that's just a function of r. And so what you do is, to solve this Schrodinger equation, you know, solve this business, what you do is you postulate that, you know, you have your psi, your wave functions that, you know, solve the Schrodinger equation. Now we know that we have to diagonalize this piece, so they're going to be labeled certainly by L and M, the quantum numbers corresponding to, you know, angular momentum, and, you know, in spherical coordinates, you got that. And the form of this has to be a piece that is diagonalizes this, so it's proportional to the y-elements. And the leftover piece, now this is something to think about, right? The leftover piece must be the thing that is spherically symmetric. So we know that L squared, that operator, the thing that corresponds to this L eigenvalue, that's a scalar, so that's spherically symmetric. So in principle, whatever's left over, which is some function, that could depend on L. It cannot depend on M, because M gives you the component in some arbitrary, you know, in the Z direction, whatever that is. That's arbitrary because it's spherically symmetric potential. So that part of it that function, the leftover piece can't depend on M because that's not spherically symmetric. And we know that we already taken care of the how the thing rotates by choosing these YLMs. We already know what the M dependence is. That gives us how the states rotate. And so anything that's left over must be spherically symmetric. So whatever it is, it's some function of R, right? Or sorry, of R. So it doesn't depend on theta and phi, because these are also dependent on the definition of the z-axis, right? They're the spherical coordinates away from the z-axis. So this is all the angular part, right? It has to be taken care of by the eigenstates of this guy. Everything else has to just depend on little r, the radial coordinate. And the only subtlety is that that eigenvalue corresponding to L squared, that thing is spherically symmetric because it's a scalar. So this F could also depend on this eigenvalue L. That's the general form. And now the only other thing is that you've got this pesky 1 over R running around here. And that's and you got this R over here, and that's a little bit annoying. So the way to get rid of that is you just, instead of calling this F, you call it some other function U sub L as a function of R divided by R. And these are the YLMs. And this is the general solution to any spherically symmetric potential. And now you can substitute it in and see what the differential equation is, right? You can substitute it into here. Any questions though before I do that?
No, I mean, they go over that pretty in depth there in E and M. You know what you just showed.
Huh?
That's really helpful.
Oh, okay. Well, that's good. So let's try it. Let's act with H on this new psi LM that we have defined. What do we get? We get minus 1 over 2m. You get 1 over r, 2 derivatives with respect to r. And now this, you'll see this very convenient u over r gets multiplied by r. So this just becomes a u sub L. And of course, multiplied by the YLM. But the r derivative doesn't act on the YLM, so it's okay. Then what do you have? Well, then you have the L squared part, right? You got this guy right here. That gives you L plus 1 over 2m. You've got this r squared right here. And then of course you have the v of r. And all of this is multiplying u L over r, right? That's this guy. And then of course you still have the YLM. And that's all supposedly equal to the energy, right, that we're looking for. And there's in general going to be a different energy for each L. Again, because this part, the L is spherically symmetric portion. It's the magnitude of the angular momentum. So that, you know, the E could depend on L for sure. It can't depend on M. And yeah, it's annoying, you got 2 M's here. This is a mass, obviously it's a mass. And of course, this is the M angular momentum mass. So, okay. So the E could depend on L. And you've got the U of L over R and YLM. So you see, of course, the YLMs all drop out because, well, I mean, that's how we chose the solution, is to diagonalize the L squared part, the angular part. So you see that all the Schrodinger equation reduces to just a one-dimensional equation, right? And I remember, you did this homework where you had comparing a square well with a a well with like an infinite side. That well with an infinite side is actually just a spherical well, as it turns out, for a particular L sector. So let's talk about that a little bit. So, okay, so now you see also the 1 over r's cancel. There's a bunch of 1 over r's here. So in the end, what you get is minus 1 over 2m, two derivatives with respect to r, plus L plus 1 over 2m r squared, plus v of r, all acting on u of L, r, is equal to E of L, u of L of r. A single equation, a single one-dimensional equation for u. So you see, this 3D problem that we started with reduces to a 1D problem for this wave part of the wave function u, where it looks just like a 1D problem, except you have a different kind of potential. You have your original potential plus this centrifugal term. And you also, but it's, you also have for each value of L, each angular momentum quantum number, you have your own little 1D problem you have to solve. You see, for the higher angular momentum, what happens is this term, right, becomes more important. And what this term looks like in terms of a potential, right, it's if you plot this thing, if you call this sort of an effective potential, right, as a function of r, this thing, it blows up at the origin. So it kind of gives you a potential that this is the sort of L plus 1 over 2m r squared. It gives you kind of repulsion away from the origin. So the higher order, the larger the angular momentum is, right, the more the state wants to push away from the origin. It sort of makes some intuitive sense, it's whipping around faster, pushes away from the origin. And that's captured by this effective potential, right? For each wave function, at a particular L, you'll have this effective potential where it's your original potential plus this kind of repulsion due to the angular momentum, the centrifugal part, which looks like this. So it's like you'll get a combination of the two kinds of the original potential in this part. But otherwise, it looks just like a 1D problem, right? Remember, 1D is minus, and we can restore back the h bar squared if you want. Yeah. But remember, the 1D problem is just this. And now we see a spherically symmetric problem is just like the 1D problem, except there's a separate 1D problem for each angular momentum value L, and the potential is modified in this way. And the various solutions here for L is equal to 0, 1, 2, and so on. These are called the partial waves. And sometimes they're given letter names. This is called the S, this is the P, D, just like the orbitals. We'll talk more about that next semester, but yeah, so this is how you would solve a radially symmetric potential. And this part is something, it's called the centrifugal barrier. Right, it prevents the state from going to the origin. Okay, any questions about that?
Yeah, that graph you drew, the LL plus 1 over QMR squared. Now, the direction, I see it's like a barrier from the central part, but is the arrow going downwards towards the X or the R, right? So it has a downward slope. It's not going upward, right? So it's not approaching from the right to left. It's going from left to right, right?
And this is 0.
Yeah.
It's like this.
Yeah. So it's going downwards, right?
It goes to 0 for large R.
Right, okay, that's what I thought. Right, so that makes sense, because it's 1/r² thing, and it's the potential, right? And so for large R, it's gonna go, okay, I just want to make sure. And that's the barrier you're talking about though, right?
Yeah, at higher angular momentum, the states are prevented from going close to the origin. It's a centrifugal barrier.
Yeah.
It makes a lot of intuitive sense. Larger angular momentum means the state is sort of whipping around more, so it stays away from the center.
Right.
Okay. So you can actually do the kind of, also do the bound state and scattering state kind of analysis for this. I think that's maybe what I'll do next time, but the point of next class will be to talk about addition of angular momentum. That's the next topic, next major topic, and that'll take up a whole class period. And that will sort of wrap up angular momentum. But just to give you a flavor, of course, if you have a total angular momentum and you add two of them, right? Unsurprisingly, this will have its own eigenvalue, right? And this will have its own eigenvalue like that. And it will have its own associated Hilbert spaces. So this object, you can think about it as living in a bigger Hilbert space that's just a tensor product of the Hilbert spaces of the individual component angular momentum. And that's where we're going to go next. So what we will be skipping, I guess, is the hydrogen atom. But hopefully you've seen that before, and we'll also cover it in the next semester.